This article illustrates some typical applications of operational amplifiers. A simplified schematic notation is used, and the reader is reminded that many details such as device selection and power supply connections are not shown. Operational amplifiers are optimized for use with negative feedback, and this article discusses only negative feedback applications. When positive feedback is required, a comparator is usually more appropriate. See comparator applications for further information. Practical considerations: operational amplifiers parameter requirements. In order for a particular device to be used in an application, it must satisfy certain requirements. The operational amplifier must have large open-loop signal gain, and have input impedance large with respect to values present in the feedback network. With these requirements satisfied, the op-amp is considered ideal, and one can use the method of virtual ground to quickly and intuitively grasp the behavior of any of the op-amp circuits below. Those interested in construction of any of these circuits for practical use should consult a more detailed reference. See the external links section. Component specification: resistors used in practical solid-state op-amp circuits are typically in the key copyright range. Resistors much greater than 1 mile copyright cause excessive thermal noise and make the circuit operation susceptible to significant errors due to bias or leakage currents. Input bias currents and input offset: practical operational amplifiers draw a small current from each of their inputs due to bias requirements or leakage. These currents flow through the resistances connected to the inputs and produce small voltage drops across those resistances. Appropriate design of the feedback network can alleviate problems associated with input bias currents and common mode gain, as explained below. The heuristic rule is to ensure that the impedance looking out of each input terminal is identical. To the extent that the input bias currents do not match, there will be an effective input offset voltage present, which can lead to problems in circuit performance. Many commercial op-amp offerings provide a method for tuning the operational amplifier to balance the inputs. Alternatively, a tunable external voltage can be added to one of the inputs in order to balance out the offset effect. In cases where a design calls for one input to be short-circuited to ground, that short circuit can be replaced with a variable resistance that can be tuned to mitigate the offset problem. Operational amplifiers using MOSFET-based input stages have input leakage currents that will be, in many designs, negligible. Power supply effects: although power supplies are not indicated in the operational amplifier designs below, they are nonetheless present and can be critical in operational amplifier circuit design. Supply noise: power supply imperfections may lead to noticeable deviations from ideal operational amplifier behavior. For example, operational amplifiers have a specified power supply rejection ratio that indicates how well the output can reject signals that appear on the power supply inputs. Power supply inputs are often noisy in large designs because the power supply is used by nearly every component in the design, and inductance effects prevent current from being instantaneously delivered to every component at once. As a consequence, when a component requires large injections of current, nearby components can experience sagging at their connection to the power supply. This problem can be mitigated with appropriate use of bypass capacitors connected across each power supply pin and ground. When bursts of current are required by a component, the component can bypass the power supply by receiving the current directly from the nearby capacitor. Using power supply currents in the signal path, additionally, current drawn into the operational amplifier from the power supply can be used as inputs to external circuitry that augment the capabilities of the operational amplifier. For example, an operational amplifier may not be fit for a particular high-gain application because its output would be required to generate signals outside of the safe range generated by the amplifier. In this case, an external push-pull amplifier can be controlled by the current into and out of the operational amplifier. Thus, the operational amplifier may itself operate within its factory-specified bounds while still allowing the negative feedback path to include a large output signal well outside of those bounds. Amplifiers: we begin these examples with that of the differential amplifier, from which can be derived many of the other applications, including the inverting, non-inverting, and summing amplifier, the voltage follower, integrator, differentiator, and gyrator. Differential amplifier amplifies the difference in voltage between its inputs. The name differential amplifier must not be confused with the differentiator, which is also shown on this page. The instrumentation amplifier, which is also shown on this page, is a modification of the differential amplifier that also provides high input impedance. The circuit shown computes the difference of two voltages, multiplied by some gain factor. The output voltage, or, expressed as a function of the common mode input VCOM and difference input VDIF. The output voltage is. In order for this circuit to produce a signal proportional to the voltage difference of the input terminals, the coefficient of the VCOM term must be 0, or. With this constraint in place, the common mode rejection ratio of this circuit is infinitely large, and the output, where the simple expression RF/R1 represents the closed-loop gain of the differential amplifier. The special case when the closed-loop gain is unity is a differential follower, with inverting amplifier. An inverting amplifier is a special case of the differential amplifier in which that circuit's non-inverting input V2 is grounded, and inverting input V1 is identified with VAN above. The closed-loop gain is RF/RIN, hence. The simplified circuit above is like the differential amplifier in the limit of R2 and Rg very small. In this case, though, the circuit will be susceptible to input bias current drift because of the mismatch between R1 and R2. To intuitively see the gain equation above, calculate the current in RIN. Then recall that this same current must be passing through RF, therefore. A mechanical analogy is a seesaw, with the VAR node as the fulcrum, at ground potential. VAN is at a length RIN from the fulcrum. VOUT is at a length RF. When VAN descends below ground, the output VOUT rises proportionately to balance the seesaw, and vice versa. Non-inverting amplifier. A non-inverting amplifier is a special case of the differential amplifier in which that circuit's inverting input V1 is grounded, and non-inverting input V2 is identified with VAN above, with Rg per 2. Referring to the circuit immediately above. To intuitively see this gain equation, use the virtual ground technique to calculate the current in resistor R1. Then recall that this same current must be passing through R2, therefore. A mechanical analogy is a Class II machine, a lever, with one terminal of R1 as the fulcrum, at ground potential. VAN is at a length R1 from the fulcrum. VOUT is at a length R2 further along. When VAN ascends above ground, the output VOUT rises proportionately with the lever. The input's impedance of this simplified non-inverting amplifier is high, of order RDIF, AOL times the closed-loop gain, where RDIF is the op-amp's input impedance to differential signals, and AOL is the open-loop voltage gain of the op-amp. In the case of the ideal op-amp, with AOL infinite and RDIF infinite, the input's impedance is infinite. In this case, though, the circuit will be susceptible to input bias current drift because of the mismatch between the impedances driving the V+ and VAR op-amp inputs. Voltage follower. Used as a buffer amplifier to eliminate loading effects. Due to the strong feedback and certain non-ideal characteristics of real operational amplifiers, this feedback system is prone to have poor stability margins. Consequently, the system may be unstable when connected to sufficiently capacitive loads. In these cases, a lag compensation network can be used to restore stability. The manufacturer data sheet for the operational amplifier may provide guidance for the selection of components in external compensation networks. Alternatively, another operational amplifier can be chosen that has more appropriate internal compensation. Summing amplifier. A summing amplifier sums several voltages. When, and independent. When outputs is inverted, input's impedance of the nth input is, instrumentation amplifier. Combines very high input impedance, high common mode rejection, low DC offset, and other properties used in making very accurate, low noise measurements, is made by adding a non-inverting buffer to each input of the differential amplifier to increase the input's impedance. Oscillators, Wien-Bridge oscillator. Produces a very low distortion sine wave. Uses negative temperature compensation in the form of a light bulb or diode. Filters. Operational amplifiers can be used in construction of active filters, providing high pass, low pass, band pass, reject and delay functions. The high input impedance and gain of an op-amp allow straightforward calculation of element values, allowing accurate implementation of any desired filter topology with little concern for the loading effects of stages in the filter or of subsequent stages. However, the frequencies at which active filters can be implemented is limited. When the behavior of the amplifiers departs significantly from the ideal behavior assumed in elementary design of the filters, filter performance is degraded. Comparator. An operational amplifier can, if necessary, be forced to act as a comparator. The smallest difference between the input voltages will be amplified enormously, causing the output to swing to nearly the supply voltage. However, it is usually better to use a dedicated comparator for this purpose, as its output has a higher slew rate and can reach either power supply rail. Some op-amps have clamping diodes on the input that prevent use as a comparator. Integration and differentiation. Inverting integrator. The integrator is mostly used in analog computers, analog to digital converters and wave-shaping circuits. Integrates the input signal van, T, over a time interval T, TO, T, T1, yielding an output voltage at time T equals T1 of, where Vout, TO, represents the output voltage of the circuit at time T equals TO. This is the same as saying that the output voltage changes over time TO. T1 by an amount proportional to the time integral of the input voltage. This circuit can be viewed as a low-pass electronic filter, one with a single pole at DC and with gain. In a practical application one encounters a significant difficulty. Unless the capacitor C is periodically discharged, the output voltage will eventually drift outside of the operational amplifier's operating range. This can be due to any combination of the input van has a non-zero DC component, input bias current is non-zero, input offset voltage is non-zero. A slightly more complex circuit can ameliorate the second two problems, and in some cases, the first as well. Here, the feedback resistor RF provides a discharge path for capacitor CF, while the series resistor at the non-inverting input RN, when of the correct value, alleviates input bias current and common mode problems. That value is the parallel resistance of RE and RF, or using the shorthand notation. The relationship between input signal and output signal is now. Inverting differentiator. Differentiates the signal over time. This can also be viewed as a high-pass electronic filter. It is a filter with a single zero at DC and gain. The high-pass characteristics of a differentiating amplifier can lead to stability challenges when the circuit is used in an analog servo loop. In particular, as a root locus analysis would show, increasing feedback gain will drive a closed-loop pole toward marginal stability at the DC zero introduced by the differentiator. Synthetic elements, inductance gyrator. Simulates an inductor. The circuit exploits the fact that the current flowing through a capacitor behaves through time as the voltage across an inductor. The capacitor used in this circuit is smaller than the inductor it simulates and its capacitance is less subject to changes in value due to environmental changes. This circuit is unsuitable for applications relying on the back-emp property of an inductor as this will be limited in a gyrator circuit to the voltage supplies of the op-amp. Negative impedance converter. Creates a resistor having a negative value for any signal generator. In this case, the ratio between the input voltage and the input current is given by. In general, the components, and need not be resistors. They can be any component that can be described with an impedance. Nonlinear, precision rectifier. The voltage drop VF across the forward bias diode in the circuit of a passive rectifier is undesired. In this active version, the problem is solved by connecting the diode in the negative feedback loop. The op-amp compares the output voltage across the load with the input voltage and increases its own output voltage with the value of VF. As a result, The voltage drop Vf is compensated and the circuit behaves very nearly as an ideal diode with Vf equals 0 V. The circuit has speed limitations at high frequency because of the slow negative feedback and due to the low slew rate of many non-ideal op-amps. Logarithmic output. The relationship between the input voltage and the output voltage is given by where is the saturation current and is the thermal voltage. If the operational amplifier is considered ideal, the inverting input pin is virtually grounded, so the current flowing into the resistor from the source is where is the current through the diode. As known, the relationship between the current and the voltage for a diode is this, when the voltage is greater than 0, can be approximated by putting these two formulae together and considering that the output voltage is the negative of the voltage across the diode, the relationship is proven. This implementation does not consider temperature stability and other non-ideal effects. Exponential output. The relationship between the input voltage and the output voltage is given by where is the saturation current and is the thermal voltage. Considering the operational amplifier ideal, then the negative pin is virtually grounded, so the current through the diode is given by when the voltage is greater than 0, it can be approximated by the output voltage is given by other applications. See also, current feedback operational amplifier, frequency compensation, operational amplifier, operational transconductance amplifier, transimpedance amplifier, notes. References. Further reading, Basic Operational Amplifiers and Linear Integrated Circuits. 2nd ed. Thomas L. Floyd. David Bakilla. 593 pages. 1998. ISBN 978-0-13-082987-0. Design with Operational Amplifiers and Analog Integrated Circuits. 3rd ed. Sergio Franco. 672 pages. 2002. ISBN 978-0-07-232084-8. Operational Amplifiers and Linear Integrated Circuits. 6th ed. Robert F. Corlin. 529 pages. 2000. ISBN 978-0-13-014991-6. Op-amps and Linear Integrated Circuits. 4th ed. Ramgar Awkwad. 543 pages. 1999. ISBN 978-0-13-280868-2. Op-amps and Linear Integrated Circuits. 1st ed. James M. Thiel. 640 pages. 2001. ISBN 978-0766817937. Op-amps for Everyone. 1st ed. Ron Mancini. 464 pages. 2002. Texas Instruments SLOD006B. Small Signal Audio Design. 1st ed. Douglas Self. 556 pages. 2010. ISBN 978-0-240-52177-0. External links, Op-amps for every ANA PDFA, 1.96 MB, Single Supply Op-amp Circuit Collection A PDFA, 163 KIB, Op-amp Circuit Collection A PDFA, 962 KIB, a collection of amp applications A PDFA, 1.06 MB, AA Euro Analog Devices Application Note, Basic Op-amp Applications A PDFA, 173 KIB, Handbook of Operational Amplifier Applications A PDFA, 2.00 MB, AA Euro Texas Instruments Application Note, Low Side Current Sensing Using Operational Amplifiers, Log Anti-Log Generators, Cube Generator, Multiply Divide. AMP A PDFA, 165 KIB, Logarithmically Variable Gain from a Linear Variable Component, Impedance and Admittance Transformations Using Operational Amplifiers by D. H. Scheingold, high-speed amplifier techniques very practical and readably in a Euro with photos and real waveforms, single supply op-amp circuit collection, properly terminating an unused op-amp.